So we're backtracking a little bit because I updated a few things. The first thing I updated is the beautiful information over here, like local density chain. This is the local density chain. This is the mass flux divergence. Over here, there's inertia and acceleration term, which you can get the local acceleration, the convective acceleration, pressure, viscous term, body forces, and if you want to like even more showcase this shear viscous term and compressibility plus bulk viscous term at the body. And also pressure gradient term. Wanted to kind of showcase it a little bit more because last time I believe we left off in this case over here, which shows beautiful but doesn't show why. It means I derived this but didn't show. Oh, and also this is from. Oh, let me just say Dr. Schmidt. Yeah. I'm going to update this a little bit more probably, but for now, this is from Dr. Schmidt's notes, which proves and showcases this thing over here, why that appears, kind of. Angular deformation strain rate kind of implies by just showing what that means, why we get that. And you see the 1/2 gradient v plus parentheses the transpose of that, which is basically that over here. So it is related to the angular deformation, and we will eventually showcase it a little bit more, but we're not really going to that state right now. So I'm just going to showcase it a little bit, but we're going to move on real quick. So over here we have the definitions of the this energy one. So fun fact, the energy one I'm using Dr. Um, Sanchez's way of doing it, which is basically using a small e, which is the Pacific version. Pacific energy to me is much easier for me to memorize. That's the reason, but no other reason than that. And then there's a heat divergence, there's a viscous dispersion, there's energy work, pressure work, and then there's the rate of energy. Yeah, the same thing. Honestly, I should probably start remembering the big E version because I feel like a lot of classes use the big E instead of the small e. But either way, I like the small e because it's more, in my opinion, compact. But I probably should get used to this big E. Either way, there's a Lagrangian follows a particle, and Eulerian. We'll use Eulerian a lot because it's much easier to follow the particle. I think last time we discussed this, but because the velocity and static terms are nothing, you can delete all of the velocity terms over here. Velocity, if it's velocity, you can get rid of it, and giving this version over here. Now, this version is kind of universal. Um, Now, this B is a vector, and a lot of times either minus GEZ, but we see a case later on that I think we did explain that was not that, and that's because it is having another acceleration to the whole body this way or that way. I think it's that way, which has a reaction force on the liquid going this way or something, which we'll see soon. I think we already did that though. But this one is basically just using Bernoulli, honestly. You don't know Bernoulli yet, but we're shortcutting the Bernoulli by taking out the velocity of saying static. And I think we did this question already, but it's good to review. So in the end, we get this. We just plug and chug after we get we integrate those, and you get this fluent form, which kind of showcases if it's over here. If it's here, it doesn't matter because this thing over here goes to the same space. But over here, you see the H2 matters, and then I think this is generated incorrectly because H1 is like over here. Wow. Um, what a weird what a weird situation. But yeah, but H2 A minus H1. Okay, I think it generated incorrectly. Don't worry about that. But as soon as you get that form over here, oh no, 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 it didn't generate correctly. This thing over here is oil over here, which is the pressure over here, and because gas is less pressure resistant, who cares about the gas? That's what happened. Yeah, now I remember. So you can see what was this called to get determined the reading pressure in the gauge. So it makes sense. You have an opening over here. We need the pressure over here, then pressure back over here with the oil instead of this what is it called Hg. Which is, I don't know what Hg is. I need to look at the PR table. Okay, so Hg over here, we get this, which we add. And then honestly, if you do Bernoulli, you would probably have done this equals P air plus density oil, GH2 plus, well, oil, instead of doing this way. I did it this way. Because you can. Because if you were trying to think of it without Bernoulli, you would have had to say this integral over here is constant. So you can kind of imagine that for this ATM, you're adding this, and then you're going over here. This doesn't matter because you add it and then subtract it. You're going up, which is subtracting, and then you're going up again, which is subtracting again, which is how I kind of showcased it. But if you use Bernoulli, it would be a little different, but that's kind of how I showcased it. Again, we do the same thing. We get this form, which is a beautiful static version. And I think this is the same question, if I remember correctly. I don't think this has anything different. Yeah, this is just Bernoulli again. Yeah. I don't know why they use a flow rate here. Yeah, really didn't matter for this question unless I did it wrong. Okay, so we're good. Yeah. Yeah, I don't see any problems with this one. This one is just figuring out, determine the PA minus P, the difference, pressure difference, which we can just figure out by saying, well, PA1 is basically, pen up, PA1, and then minus that, and then plus PH2 over here. So you kind of see over here PA1, and you were asking for the difference between this and this. So in this case, depends on how you frame this, but if you're going for PA and going upwards, you're minusing, right? And then you go over here, and then pH2 is this is minus, and then you delete these things, these are useless, and then you add this amount, which is H2, which H1, you add it, and you plug into here and grab this kind of version over here. Not overly impossible, but requires some thinking. Yes, and if I remember correctly, we did something. Yeah, I think what I did was to get a rho to G, which equals alpha, gamma or something, which is 2 over here, which is 15, because you gave us gamma over here, so you have to do it this way, which means I could have done one more step, make it easy for you to understand, but I was lazy. Literally was lazy. Ah, this question. Yes, this is when we added velocity, I remember. So we added a v and a u, and we did all these simplifications because this is very simplified. And even with the simplification, it's like a bunch of things. You assume steady state, assume liquid, assume laminar, assume fully developed one-dimensional flow, assume Newtonian laws of viscosity, assume no friction, no slip condition, assume no pressure gradient in the x direction. So I'm shocked I didn't say assume invested because oh yeah, it's not invested, right? It's viscous. It has a viscous force. Yeah, I'm shocked that it doesn't have that though because uh I might have accidentally done that because of how many assumptions, because I was just copying and pasting assumptions basically. So, anyways, with that said, you cancel out all the ones that was steady state. With that said, you can see that we are getting into this form over here, which is going to be just the divergence of V. Uh, yeah, I think that's correct. Anyways, with that said, we have continuity. And in liquid, like 80% of the time, it is a constant thing. The reason I don't say 8, I don't say 100 or 90 is because I remember in 210C, there is oceanography that has a different type of temperature varying pressure, and that's very powerful later on. So I don't really say that ever, 100%, I guess. Even 80% is like a little bit too much. Anyway, with this term, you can get rid of this. This is one way of getting rid of the one of the bulk viscosity term. That was the reason why I was like thinking, why is this not gone? But this term has to stay, although that's what we're going to cause this kind of movement over here. Anyways, with that said, you can kind of simplify because of all the one-dimensionalists, and I think I already said that last time, and the v equals 0. Apply it to here, and you get this form, fully develop. And this is Navier-Stokes. Navier-Stokes, you simplify again because no pressure gradient in the x direction, which implies basically, if you look over here in x, you change delta x, right? The velocity stays the same, right? There's no difference between this velocity and this velocity over here. Endless parallel plate, remember? And also the fact that, you know, if you look at this, the G term is here. Yeah, it's unilateral basically. But well, that's how we got the U. And then this integrate over here to these two forms, and this integration led us to figuring out these boundary conditions, and this boundary condition we plug it in to get these formats. Clean set. We do that, do a little bit of shifting. We get tau because tau in the middle must be equal to each other just because of continuity and physics, how that works. Kind of, I remember that there's some, I'm not talking about it. We don't have to talk about that case. There's an easier way that Dr. Sauer did. After that, we indicated that we can do this again with this format over here. We simplified again to this because it's static again. All the velocity gets deleted, and I just realized why the hell is that shifted over? This is not the first time I'm recording this. There's so many mistakes on my stuff that I have to keep on recording it. And I got lazy at one point and stopped doing the whole entire like any of the sometimes I just screenshot the professor's notes because I got lazy. I was gonna redraw all this stuff and I was like, no, I'm not doing that. Either way, at the point of this question, I found was to get your idea of trig involved here because you need the trig to get this height over here, which gives you this form. And then another claim over here is that the gas over here is less like impactful than the liquid that they have, which is why we put this thing out to make this equal. I think that was the question, or they'll derive this thing, which is what I did. But generally speaking, the whole point of this is to get your mind thinking of trig again. Literally, is what my point is. Fun fact: that's the reason I went to this next because the trig was in there. Now we're going to more trig, and that's kind of there's a pattern and way I made this so that one of and the real reason I'm making this for my brother, I'm just going to teach him the whole thing in one day or 2 days, 3 days probably. This one will take 3 days. I'm condensing like 15 classes now to 4 classes basically. So I made this and we're not done. I'm gonna keep on editing it for the next 5 or 6 days. I don't know how long, and then until it becomes perfect, and then I'm gonna go to my brother and then teach everything there. Anyways, with that being said, this is just a prototype. Anyways, I think I explained this. I think I already did the force in all and how this came about to be. I think I have done this part over here, which is the bar C. You can see over here how it turns out. We did this over here, I believe. Yeah, with the moments, yeah. And then we got into here. I believe this is the first 10 question, which is basically me doing all the derivation over here and then saying that we have to use it now. Fun fact, if I remember correctly, oh yeah, it's still the same equation, but basically, wait, this is a mistake over here, right? No, it's not. That's correct. Anyways, you see the change of the B over here because we did a coordinate change, so you can kind of see both the uh y direction and the x direction has a force now that causes this to happen. Kind of a little confusing how I showcased it, but you can see with that these form and the power centroid show up, which I'll be honest with you, very interesting that they showed a centroid. You see, here's the thing. After fluid statics, they usually don't show how it connects to Navier-Stokes, but I like showing it with Navier-Stokes. So we'll always go back to Navier-Stokes just because we can showcase it. I feel like everything needs to circle back a little bit to showcase it, but it's hard to find a place to do it because if you think about a class, showing off Navier-Stokes right away is like, whoa, why are you giving me this hard stuff right now? And it makes I don't know. I think some students, some of my fellow classmates would genuinely like not like it, but in my opinion, Navier-Stokes should be the first thing to derive because it's everything in fluid. It is the king, queen, the only thing that exists in fluids that makes sense after you learn it. Like to me, once you learn Navier-Stokes, everything else is just how in the hell do you go back to Navier-Stokes from this? How in the world did you derive this from Navier-Stokes? That's my question always. And this is always question my head always goes to when I think of fluids. Like, how did you do this? And how did you modify Navier-Stokes to get this? How did you add something to Navier-Stokes to get this? What kind of forces did you add to Navier-Stokes? What did you do? It's always my question. And that's the reason why I think Navier-Stokes is the first thing that should be taught, and everything should be derived from it, which is what I'm doing. Anyway, that's my opinion. Anyways, sorry about that discussion. I think we already did this, but remember statics, these centroids over here, you get this kind of, I think we have done this like 16 times, so why am I explaining to you again? It's like the 16th time I'm explaining to you. All right, anyways, the moment thing I explained to you. So this is the fourth question over here, and we realize that there's a dpy sign, and then you can get an integral, we get this form over here. With that said, dpa sign. So you actually we can already plug into here. I think I did a shortcut. Here it is. This over here, if I remember correctly, is AY bar, and AY sign sling equals to YC, which is this bar over here, and which gets you to this form, and now it's just a plug and chug to get YC, and then you add it to the height over here. D divided by 2 sine 50 over here, because this angle is 50, so you need to sign it up. It's not anything too drastic. It's basically just plug and chug, if I remember correctly, this question. All right. Next question. Oh, it's getting the h over here, if I remember correctly, which is just doing Bernoulli again. I showcases this again because we're going from this coordinate back to regular coordinates, so it's just integrating and getting this. And then I didn't even show the g, h over here, but you can see that we canceled the velocity terms, and I didn't cancel out this. I keep on finding like 16 mistakes in my stuff. I do enjoy that I find these mistakes at least. Imagine not finding these mistakes. Either way, I'm sharing it to everyone, so eventually someone will send me like 16 mistakes I made. Anyways, with that said, we have an isotropic triangle, and this question actually came from the textbook Fluid Mechanics by Frank M. White. If you want to check that one out, it's a great book. Another great book is that I'm following. This is more undergrad stuff, but it's Fundamental Fluid Mechanics by Monson, Young, and Oshikishi. Another one you can want to follow is basically Elemental Fluids Dynamic by DJ Action. Another one you can follow is textbook by Punesh K. Kuda, Ira M. Coleman, and David R. Dwalling, Fluid Mechanics 6th edition. Or you can also follow Fox and Fluid Mechanics Introduction to Fluid Mechanics 8th edition. That one I don't like too much. I still use it, but not my favorite. What else? There's a bunch of fluid books here. Introduction to Plasma Physics. No. Introduction. Yeah, there's a bunch of books here. Back to Deep Transfer. Yeah, there's a lot of fluid textbooks here, but generally speaking, those are the ones I would recommend truthfully to you. There's a bunch of other books, and you can check them out. But I've found those three to be really good. For learning regular fluid dynamics, we'll go to the further versions maybe later. I mean, not probably not in the summer, but when we have time. Oh, by the way, this P over here is angle, so make sure to get that angle in. That's because it asks for the horizontal P force. That's going to equalize it for equilibrium. This question is quite interesting because you go through the same whole process of getting HC and everything, and then doing the moment IG again, and then you use statics, which is interesting because you're going to do an equilibrium of this point because this P has a force, and you need to equalize it with whatever P force you have, which gives you this. Interesting question. In my opinion, this part fuses is trying to fuse statics with fluid mechanics, which is interesting, but again, you're to follow it. Okay, the static acceleration X direction, in my opinion, this is beautiful because I think we did this question, honestly. We have acceleration over here, but it actually, the fluid experience acceleration this way, which causes you to do a negative effective, a negative G, which goes over here, and you plug into the simplified dynamics again, but this time we have Bx and Ag, so both of them has a pressure. We integrate it, and the constant is not a constant. You need to do Fz over here, so to care about the other side. And when the other side gives you a question, you add those two up to get something, which is the first time you guys have been introduced to like scalars must be a scalar. So both of these must be valid. The pressure must work for both, and which creates this thing, which creates this kind of showcase over here. Another way to do a pressure must be both is to cross derivatize it. Very powerful move that a lot of people do, and then you get this form over here, which is beautiful. But and then there's projection because you need to care about curves sometimes, and then because of the projection, there is something called a vector in the area because the pressure doesn't have a vector, so the area must have a vector. So you get something like this thing, which gets you into this kind of hijinks. But the beautiful part is Fy is basically just a weight on top, which is beautiful because the projection works like that. And you can kind of see with the other one that it doesn't. It might be really weird at first, but it makes sense once you think about how the projection works. Because where the cosine goes, you can imagine you're capturing all this space and you're catching all this space. So this space, you have to get a centroid. This space is just having a force downwards there. And but this also is a force downwards, but it's also in the centroid of that force. So it is very interesting because once you do the math over here, it showcases over here the x direction centroid because of how it turns out to be. This is extra over here, and not part of the question, but I thought it was interesting enough to put in here because it's kind of interesting why they chose this point. In my opinion, probably not as valuable because the question doesn't ask for it, so it must be less valuable somehow. I don't know why. Anyway, we do buoyancy force. Oh, I don't think that we talked about this one although. So again, actually, we can emphasize by just looking at this y direction. You can see where the buoyancy comes. But here's how the general idea is. This force is, you see this symbol? So you're doing a force diagram up to here and then back to here. And you can see that is where it comes from. And the x direction should cancel each other because you did a loop over here. And there's nothing really different from here to here if you do a projection. So in that case, the weight over here is what matters. And that weight difference is called the, I never really said it here. Why did I not say it? Architect's rule or something. Let me grab that because I don't remember how to say it, but it's some rule that you can claim. Honestly, I didn't use a lot of buoyant force, I guess. Don't like how I didn't put that there. Anyway, so hydrodynamic force over here. Now, this is from Dr. Sakar. Let me just write from Dr. Sakar. Now, as you can see, what is this? We should go back a little bit. I hate that I don't know how to say that properly, honestly. So I'm going to find how to say it properly real quick in one of these textbooks. Because I know for a fact where it is. I read this textbook multiple times now. Yeah, that's actually kind of weird how many times I've actually read this one. Anyway, Archimedes, and this is called Archimedes principle. Go John, find it. And that didn't even take that long to find. It took like 6 seconds because I know where it is. Anyways, with that, yeah. So Archimedes principle, yeah. Anyways, with that said, we do hydraulic jack principle, which we again get into this form over here. You might be saying, how the hell did you get this? And this is actually the first time you get introduced to a boundary condition. So over here is P over P and PA. So P over PA looks like the pressure is already given. Now, I will say this. Right now we're saying P1 equal P2 for now. But you can imagine if the pressure increases over here and the area increases, and then the pressure has to like increase, and if the area stays the same, it's a little different in the different cases. But in general, if this is true, you can get this. But if this is not true, then you have to rethink this. But a general idea is this case over here. And how do you get this case? You might be asking. We do integral, right? We get integral and we get P equal minus rho G, right? With H over here, which is H is the difference between the two fluids, and we did Y1 minus I2 to indicate that. And then we have a plus C, right? That plus C is our boundary condition. And you can imagine how that would work a little bit because for now this pressure must be same. So you can say at P at H it must be I think F2 minus A1 minus F1 minus A1. So that is how C comes in, and you get this form over here. Yeah. Anyways, not really anything difficult, but it's just interesting how that turns out. And then this could be the extra H force in between if you have something like this happening. And indication over here, we have to say that this is true a little bit for this to work, but that's not my problem. Anyway, in general speaking, just listen to this, what they said, because honestly speaking, I was reading this and saying, yeah, that's perfect. There's no real change. There's no need to change it. Yeah. And then we go to temperature variation in standard atmosphere. So you can imagine if you're doing, I assume this, and last time I remember saying like, hey, if you assume this, you have to assume a bunch of other things, but we still assume it, even if it's not possible to assume. You know why? Because it's still one of the easiest and best indicators of gas. Sorry to say it, but even though it's pretty, I mean, pretty bad, like 10% or 15% error when you do a CFD with it, it is easy, it's cheap. So they still use it. Anyways, with that being said, we should probably do this integral. And if you do this integral, you get this over here. And this is with constant p, and you can imagine what happened, right? You just do separation of parts and just do that integral. Over here is a decreasing thing, so if pressure is decreasing, you put it into here and get this form over here. Why is that happening? It's because this is tropospheric, this is this, and this is this, and this is this. They're showing the stratosphere region, which is a estimate by a constant temperature, and a decreasing region like this, which by decreasing it could be also increasing, just how it shows up. But you got the point over here. With that said, oh, this question, right? This question actually probably should have been in one of the earlier ones, but so I just wanted to showcase that as a triangle, so it starts from 0 and goes to this. And I realized that, oh shit, I haven't showed that earlier. So I just showed it up here. It's the same math, the same principle. I just forgot. I should probably move it up, but it's kind of funny now, so maybe not. But in reality, I should probably move this up to earlier because it's kind of weird to be here, you know. Before all this stuff, it should be like maybe like even above this. Yeah, it should be like way up here. It should be like over here. When we start doing this, it should be the first question because it's actually one of the easier questions to understand. I mean, not easier, but one of the more visually appealing cases of why this thing is a triangle. So if you have something like this, I don't know, like this, you can kind of see that even if you do a vertical projection, it'll still be like, you know, the projection version of it. It's just I forgot to showcase it. Literally just forgot. So there you go. Anyways, we're moving on to here again. I think this is a mistake. I think it's one slide over. Yes. So we're doing analysis to get Euler's, a beautiful Euler. I used to call it Euler or something weird like that. I never got corrected until later on in my career. I was like, I called you the Euler for so long. It's Euler, God damn it. And I was like, fuck, how oblivious am I? Every single professor said Euler, and I said Euler for some reason. Anyway, there's two ways to do this. I like one way better than the other way. One way is to do characteristic value like this and go down the rabbit hole of doing order calculations like this. And you kind of see what it means. Like because of these characteristic values over here, L, H, and W, you plug into here, so you can kind of see what's going on. Plug into here, do all this stuff. Eventually go down, do this version. And these two ways are actually the same way, just described differently. But and also I do mention that there's a small, like if you look at the small region over here, you'll find out that basically L has is too large or the U is L is super large, its only time is valid, which means if it's close to the wall, Euler is a bad idea. It's a horrible idea, and that's what we call boundary layers. And basically, is what I describe. You can kind of look at this if you want. This is a whole rotation, but how I go about doing this is usually you got I have the slides and I gave it to you, so you can just look at this stuff and figure it out. Mostly because I want to go the easier way, which is this way. So basically, assume V, the biggest thing is U infinity. Assume gradient A is something like 1 over L. I was going to do L, but then I remember the other one used L, so I use A instead. And it's the same thing. Rho equals rho infinity. P minus P infinity is delta P. And then we have this, we do individually what they are, these terms individually. So go over here term, go over your term, go over here term, go over your term. You just go and grab whatever it is and plug into here. And then whatever this is, plug into here and get this. And then we do it constantly. And we do a division to get a non-dimensional number, and we get Reynolds number. And with that Reynolds number, if that's large, we find that the convection is important. And for FR, we'll assume that it's linear 1. So both matters. And for ST, we'll assume that both matters over here because we use a convective term like this to figure it out. So you can see over here that this is what remains. And this form I love more because it's much more intuitive of what's going on, in my opinion. Way more easier to physically make sense of. Either way, both ways indicates to us later on that there is a boundary layer and Euler is a horrible idea near the wall, basically. So there's I put four different types of Bernoulli to kind of scare people. Just joking, I wasn't. I put four different types of Bernoulli because I made a mistake and I didn't realize that this is over here. Where is it? This version of where is it? This version over here. I accidentally put this in here, but I didn't know how to pull it out, so I just called it four different Bernoulli and move on because I was lazy to fix it. Yeah. There's a lot of things that I'm just saying I could fix, but it's already a pain in the ass to make this, so just keeping it there for now. So we're calling Euler over here, so we just cancel these two out. We get this form, we get it to here, and now we have to find this identity to move on to get Bernoulli. And the identity, you have to go to index notation, basically. With that index notation, you do a lot of index notation. Basically, start from here. You plug in this because you have two of them over here, so you can get this out. Use the same identity over here to get rid of some of these terms. So, for example, J must be M in turn over here. With that said, you also take a dot product of double derivative. This is a v dot v. So you get this format over here, which figures out that this 2vm derivative of vm by dxi is the same thing, which is interesting. You would never imagine that. But in reality, why that's true is because you still have this dot process over here. This is still a dot product, which is indicated to me it really didn't make sense at first, but now it does a lot because of that dot product understanding. So there is this over here, which is the way to get it. And you can see if you divide everything by 2, you get this form. Now, with this set over here, you can do a little bit of manipulation to get this form, moving this portion outwards, which implies, because this is the same as this over here, which is same as this, which gives you this form, which indicates to me that this is equal to this. Is basically what's saying. Very convoluted way to say that those are two. Which gives a simplification. So we're gonna have to assume barometric fluid, which is a fluid that has density change depending solely on pressure. Honestly, if I was teaching this, I would rewrite by hand, honestly, while showcasing this on the screen, so everyone else can also see it, and then you're rewriting it on the board. That would be really cool, in my opinion, if that's possible. But I know that's not possible sometimes, actually often. Anyway, then we claim constant density over here to move it out and turn to this form. So over here we have this. I think I moved all the gradient to one side to get this form over here, and then we have this. I'm gonna do it with my brother, honestly. That's the whole plan. Anyways, sorry to test you with information. If you take a v dot over here and a v dot, we can do that because it's 0 over here. We find that this is case over here. This goes to 0 because of the first principle of calculus. If you don't know it, go back to this location and figure and then do a lot of stuff out to find it's not possible. But in reality, you could just say, hey, look at this. Go to first principle. Ah, yes. And Dr. Sanchez uses the first principle of calculus to make this integral 0. But very intuitively, v dot v equals 0. And then that makes intuitive guess with what's going on, in my opinion. That's the best way to like understand it a little bit without going to like calling out theorem or going to index notation. Either way, we find this over here. And this over here is integrated with a dot. So this over here must be a constant because you can't take a derivative. This is basically a derivative. And this derivative must mean if this equals 0, this has to be a constant for this to work. So you get a long streamline, basically. And then another way, if it's irrotational over here, irrotational is beautiful because you're just making this 0. And that's easy. You're doing all that bullshit earlier. So throughout irrotational, it's beautiful. In my opinion, it's one of the more beautiful ways to do it. Yeah. And to be clear, do I know this on top of my head? Bernoulli, yes, but do I know everything I've taught you, like all the deritation? No, the deritation over here, I would have to like take a second to do. Which one is it again? The Navier-Stokes deritation over here. This will take me a long time for me to get, and I probably will just have to look it up eventually because I'm not wasting time. But in my opinion, there's things to derive sometimes, but a lot of times you can just look up after you know it's true. In my opinion, the way I see proofs is once I know it, I can trust, like if it's proved like concretely, like not hand wavy like proofs, but if it's proved like verbatim, I don't really question it anymore. I just accept it as fact for now, unless some other proof like devolves and says wrong. So I just accept it as fact for now. Anyways, with that said, a long stream, and this is from the image is from Dr. Sakar too. So let me just do this real quick. Actually, I don't know where this is from, because it's technically not Dr. Sakar. It's Dr. Sakar's notation, but I don't know where this is from, so I can't really say that right now. But I still should probably say from Dr. Sakar. So yeah, there's Sakar's image of a cylinder, probably generated with CFDs or something. I doubt it's generated with potential theory because there's a vortex. All right, so a streamline is a line that's tangent to a fluid velocity. In steady flow, the particle follows the streamline. So a streamline is flowing past sphere, assume steady, inviscid flow, incompressible, follow a streamline, conservative body forces. There's a lot of assumptions with this Bernoulli. And then again, there's irrotational assumptions, which is basically the same. And this is just two different assumptions over here. You get the point. Over here, unsteady irrotation Bernoulli. This is did I already? Oh, unsteady, unsteady. So here is a powerful idea. It's called a potential, and this potential is only possible. We'll figure out later because it's irrotational. So with this irrotational, it's like a looping definition now, but later on I'll explain why. It's because of a curl, really. And then even if it's a curl, I'm not going to actually explain that it is going to be a curl. I'm just going to showcase it a little bit, but because we need to do a streamline and potential line, but basically it is a powerful tool that allows us to do this over here, which gets this form over here, which gives you the density constant, which gives you a ball of fluid too. I forgot this form over here, which can take a gradient derivative and start changing it with time. Now, honestly, I could have done something fancy over here, the gradient over here, and then put a square over here too, but I was too lazy to do that, honestly. But that would be the more correct way to put it down, I guess, if you want to do it. So here's all the different assumptions. Yeah. There's another version of this with Mach number, but it's not called Bernoulli. It's called a category like perfect gas, other known as ones that work with ideal gas. And then you can, and then it's 212 actually. 212 can teach you it. We'll probably go through that too, honestly, because I will be thorough with teaching my brother fluid mechanics. I'm going to teach him a lot of things. Um, anyway, compressible gas over here is using this entropy version and entropy. Anyways, this thing is just from thermodynamics. Remember in thermo, I think they didn't derive it although. I don't think it's possible to derive. I think it's just found mathematically. But anyways, with that case, you find that you do the same process again, and eventually you just get this version over here with the T delta, the gradient of entropy, and so forth. A lot of times, if you do some estimation, this is possible, and we'll explain why later on, why that is possible, isentropic. But for now, you don't really know why that's possible, so I can't really say that and simplify. But for now, compressible gas, there you go. And another way to get Bernoulli, I don't like this way. This way is found by Mo, what's it called again? The textbook with Philip, no, with Moson, Young, and Okushi's thing. It's okay. It's really good for starters, but in my opinion, it really drags the idea because it requires the knowledge of using something called N, which is from dynamics, VN and VS, and this is the only time you do it. And it's not general enough for me to like say, "Yay, let's do it this way." In my opinion, no. So that's why I don't care really. If you want, if this makes more sense to you, go for it. Honestly. Anyways, with that said, we can go over here, which is the time we do some streamline and potential. So over here, you see evotationally, which gives you this potential, which allows this to happen. And how will this happen is because you already said evotational, which means the curl of the velocity equals 0. So in 2D, this must be the case. Now we said constant density, so this divergence of V must be the same. So in reality, if you plug these kind of values into here, you see you get 0. So because this is tangent to the velocity, this must be 0. And it's true, therefore it's okay. That's how you figure that one out. For the potential, is a little bit more tricky, but it's 90 degrees from the streamline, which is how you create this kind of system over here. And it works. And we'll kind of go explain a little bit of it, but if you figure out the velocity, you can imagine the gradient, right? And the gradient of the velocity, right? And the gradient of the velocity is going to be different than the tangent to the velocity, and it will be 90 degrees, and which creates this thing. So this is still assuming constant density, by the way. There's a version of it that is compressible, and this is the compressible version, and you can see the beauty of that. And then there's a 3D version here, which is more complex and requires a little bit of numerics because of this version over here. But either way, you figure it out, get it done, have it here, beautiful. Oh, fun fact, this one requires density, but this one, even without having the density requirement here, it has it works, which is kind of interesting. And it's okay, so we go into polar form over here. And polar form is interesting. You look at this and say, what can I change? Over here, you see that the change in dr does not have a change, has no physical change in the d data direction. But d data over here has a physical change with the r direction. And remember in geometric the relation over here, r d data, which is why we use the same relation over here to get it. And now there's some dot products over here, which is done by looking at the r data and r. Obviously, this is a e, which means it's going to be either 1, 0, 0, and so forth in the Cartesian plane, and 0, 1, 0, and 0, 0, 1. So you can imagine why, if it's a dot product of each other, it would be equal to 1, and if it's not 9 degrees away. So this is going to Calc 3. So this is just a little bit of definition and how to figure out this gradient. This is just a reminder because a lot of people forget and believe how they figure out this gradient, which is quite beautiful. And basically, you can get the streamline with it because how you figure out streamline is through the relationship of the gradient dot. So did I show it? No. But basically, if you get the gradient dot over here, which is supposed to be in polar form, you can. I should have done that. Why have I not done that? Oh well, I'll do that later. I did not do that apparently. If you do the gradient dot, you can get the streamline. I don't know why I did not. So this is taken from Dr. Oh my, I didn't really. Dr. Schim, uh, and then what the Sanchez. Oh, I'm spelling. So over here, there's certain I will later on explain how these are a little bit derived, and it comes from again continuity, honestly, half the time and the cross product. But you can imagine this one over here is just because it's Vx. This one doesn't need any cross product, but over here any obvious reasoning, in my opinion. But with this, we can get streamline. And the first thing we'll explain is that you can add streamline. So you can add this thing with the source, which gives you this beautiful kind of stream function, which is later on we're going to figure out that's the Rankine like thing, and you can kind of see how it's done. I kind of modeled it with this. But you can model a water pump in a river. This is beautiful. And here's another from Dr. Schmidt, the Rankine half body or oval, which is beautiful handwriting. And then if you add a sink now, you get now a oval. And now we go into if you add a source and a sink close together, you get what we call a doublet, a beautiful doublet, and you get this form over here. And if you add a flow to it, you get something called a circle, which is the first thing to start the Kudu-Kakowski theorem. Beautiful theorem, but I'll just really start doing that. Oh, I guess I should skip to here next. Which, why would I ever do that? When you have this to teach a break, and I guess it's a break from that. Monotony, I guess. I don't know. I forgot why I did it this way. Anyway, a pipette. I'll clean it up. I'll probably change the order around. A pipette static tube. I think should have been first. So This version, very key point that has to be less than 0.3. So it has to be incompressible. There's another version with Mach number that is compressible that we will cover later on, probably, hopefully. In any case, over here we find that the pressure and volume on this side, we get the velocity, that is something, and over here we get a zero. And how we figure out the zero is through these events over here. We get P static pressure over here. So we can imagine we have P static, so this goes away, and then we get this form over here. We want velocity, so you can imagine we do velocity equal this. Now, this only works for Mach number less than 0.3, so I don't know why a lot of times people think that they can do this is a velocity for static Bernoulli anytime they want, because it's not. You need to get the compressible version if you're doing real ones with supersonic or something. So this is quite interesting because some people think that this is okay. It's not okay, um, unless it's Mach number less than 0.3. Either way we call Bernoulli. I'm not going to derive this from NS again. This Bernoulli equation is we're just going to call for it because honestly, you learned this in physics 2C again, and you learned this in high school too, the Bernoulli equations. That's why everyone calls it Bernoulli. And anytime you think of fluids beyond a certain level, you always call Bernoulli because you remember from high school or your second or third class in fluid or something initially in physics. Anyways, with that said, we do the first thing. We get the velocities. We just arrange to get the V's over here. I think we arrange to get the V2, not this one. And you can imagine that V1 is 0 because it's over here, which is close to 0. I think if we say it over here. The next thing we have to do is a volume integral of the continuity equation, which is dV over here. We apply the divergence theorem, beautiful theorem. Over here we get this. With that said, you use that over here, and steady state, so this goes away. So I assume steady state over here, so this goes away. So you can see over here that's density, velocity, and an area squared, because you can imagine this normal bin over here is positive, so this must be negative going down, and there's an outside barrier over here, which also must be positive because outside is chosen to be positive. Therefore, this must be positive, and then there's area on the bottom and area on top. Density must be the same. Therefore, you get this form, which is actually called volume rate. I don't know why I didn't write down over there that it's called volume rate. And you do a little bit of simplification in A5 divided by A2. What is that? And you get this form. Okay, and then here's some factors. And honestly, for these factors to look it up, they're really, I don't think I can explain to you the reasoning for now without some kind of simulation anyways. And we're too early to do any of that. We do a little bit more pressure analysis over here. I think it's the same thing, but just a different problem. Basically just explaining that this over here is going to do like a huge entire, like, doing in and out over here and seeing that equals to Q rate. And then you use V1 and V2 and reverse engineer it with Bernoulli to get this form over here. And that's pretty much it. And you get the volume rate over here, which is beautiful. One way to do it. Here is another thing. Rotation causes some force this way, and there's no explanation yet. We'll come back to it later when we do a Magnus effect, and we're soon going to do that, so calm down. So here's another thing. There's a streamline function. This is from the book White, I believe. Is this in the velocity field of 4.0? Find it, plot it, interpret. They say plot it, but delete that. We're going to draw it because I'm not going to use a computer for this one. We can use a computer sometimes, but in reality, some questions are meant to do by paper to get your brain to understand what's happening, which is what I'm going to do with my brother, basically. Basically, what I'm actually going to do is basically this slide is supposed to be seen. The next slide is not supposed to be seen. So you're supposed to do it without looking at the next slide. So my laptop, my iPad just restarted, and for some reason I think it's out of battery, so we'll be going with no iPad. So what that means is we're going to use a mouse, which is going to be bad, but who cares? I was already looking at my iPad and seeing it's like low battery. Anyways, first thing we do is a continuity test. The continuity test is over here. You plug the U and the V in and get 0. Half the time, be careful, double check, because if you're going to the exam, there's unlikely a chance that the professor gives a non one that doesn't work, because then there's no question. The question is, hey, the trick question, there's nothing here, and that's the first question. And you see, because if it says it was 0, it would take you like a few minutes, 90 minutes to do, which means that you did something wrong. Not 90 minutes, like 20 minutes to do. And then you did something wrong because you didn't, because then you have one question that basically you're not seeing how there's more of it. I don't know how to describe it than that. Either way, you isolate the U with the streamline and then the V. And you integrate that with the same idea. And what I did over here was we have a derivative, and actually this is what White did because I just copied what White did. You take a derivative over here, and you get over here 2axy, and we see that this same thing over here. There's a negative over here, which makes it seem like that. But if you multiply negative on both sides, you get plus, which means that you can cancel this out, which means that f prime is 0, and the integral of f prime is 0 is a constant or 0. With that said, with a constant over here, you can imagine that the easiest version of that is if this is 0. And what this constant does is actually just transport this somewhere. So you can imagine it's just going to transport this whole thing to somewhere else, but that doesn't really matter for drawing this because reference frame is your choice. You make it into 0 because honestly, the real reason over here is actually just because the stagnant point over here, the origin is the stagnant point. So with the stagnant point, you can actually get instantaneous change. So you can drag over here and then move over this way because there's 0 velocity over here. So you can imagine something weird like this forming. And this is the only time like something like this can form. I think it's going this way quickly. And this was actually a test that a professor actually gave me. It's a test question actually that one of my professors gave me. Anyways, with that said, over here, you can do arctan over here, which gets 60 degrees. With that 60 degrees, you can actually now look at the certain cases. So x1 is 0 over here. Which direction is going? It's going that way because UA equals that, and the other one equals 0 because if you plug it into here, that's what happens. And you can imagine what you're doing, basically. That's all you're doing for the other questions. I mean, yeah, other directions over here. It's basically, if you know your trig well, it should be okay. If you don't know well, it's going to take a long time. Anyways, and then over here is the more interesting part because the other part is needs to be continuous, while these parts can just stick over here at 0 and transform. Everything else must follow this and must be kind of continuous. So you can imagine how this thing forms. Like they're following this thing like this because it's supposed to be continuous. Now the book shows it like this, skips a lot of steps, but over here I want to showcase what I forgot. I want to showcase something here. The origin of the stagnant point. Oh yeah, uh, a beautiful way. Like you really want examples, right? So example is like a wall over here, and you do inviscid flow over here. But again, you have to be a little far away from the wall to make this work, basically. So these things are not accurate to near the wall. Near the wall, you need to use the shear, viscous, and right now or dynamic viscosity. How do you write that? Like this? Yes, yeah. So we didn't do that yet. We do a rotational fort. Actually, we should explain what this is. So figures here is a rotational one. So rotational ones we have a triangle kind of, and this is a showcase of it. So if you have something like spinning over here like this, and this one over here is a no, this is irrotational. No, this is rotational. Sorry, this is irrotational. So irrotational, you can imagine sucking it down like a toilet. In reality, you can see that the happy face shows it off, but this over here, Rankine vortex over here, is kind of the way to model actual kind of vortex. There's a region that is rotational, and then there's a non-rotational region. With that being said, here's like a simulation I found in Wikipedia. I should probably say I found this in Wikipedia, which I'll do later. And traditionally speaking, you can see that it's by R and by 1 divided by R. So this portion over here is run by some constant, let's just say A, multiplied by R. So you can see that this is happening. This outer portion over here is ran by 1 divided by R by some kind of constant, which we'll call omega for now. And then that's it, basically. You kind of see over here, that's how it works. And with that being said, we'll move on. Oh, we have to add the dz for the polar case, so I just added that there. And then we we just do a review on calculus 3 on why this is like this. It's not anything different than what is change. It's not hardly any, yeah. Anyways, we get compressibility, cost density over here. We go down over here and realize this is 0 because this is a function of R, so it cannot be a function of theta. So we get omega c equals this, which gives you a form over here which has C. Now, we'll focus on rotational one as Bernoulli works everywhere except for the origin. So here's a streamline version, and we'll explain kind of why that it's showcased. It's actually just taking into all of this. But there's also the idea that everywhere, if you do a circulation over here, this, I believe circulation over here, this over here is 0. But if you do it in the middle over here, it's no longer going to be 0. And that is how you figure out gamma. And you'll see what I mean, I think, the next slide. So there's two conventions over here, and the professors might choose this convention or this convention. It's either way is fine. So circulation is the strength of the vortex, but you can see that you use the integral over here, and then use r d theta over here, and then you're going to actually do 0 to 2 pi. So in the middle, because that's the only where the origin exists, or only place that gamma can exist, where circulation exists. Because everywhere else is 0. This thing is 0 over here. So you can imagine over here, there's two different ways. Either one works. I believe this is actually, one way is from Dr. Sanchez, and the other way is from Dr. Schmidt. So let me just write from. Now, honestly, it's just dependent on which textbook you read. Some textbooks like that the circulation is negative. It doesn't really matter. Some circulation, it's just convention, man. Who cares, really? People may also get confused between the source and sink because they're opposite of each other. You can imagine the confusion over here. Like, hey, there's a source over here. Sink. Well, they look the same, except for this gamma, this same symbol over here. But you can see that they just invert each other, which makes sense because they look like they invert each other if you look at them. But yeah. Now, here's a Magnus effect. So if you rotate this, you're actually making a circulation, right? So if you plug in a circulation and a summation with the original doublet sphere idea, you get a force this up way, which you can figure out like a proof by figuring out what the speed and doing Bernoulli over here. And this is called the Magnus effect. And you see over here the beauty of the streamline, which is beautiful in my opinion, but this is from Dr. Schmidt. And anyways, that's why I was going back to over here because the spin force caused it to go this way, which, yeah, beautiful. And this is CFD from Dr. Sakar. Yeah. Another thing I do want to mention is for 2D volume rate, along a streamline, it must be constant because it must be the difference between one of these values with another. And if you want the proof of it, I remember there being a proof like this and doing a cross section like this and cross section like this and doing integral of it and figuring out that it must be these two. And you can do that, but honestly, it's not really that worth it. I haven't really used this, so I'm not sure how useful it is, but there probably is a use for it, which is why they still teach it. I just can't think of one yet, which is weird because I can think of most of it. Maybe, oh, wait, I think I figured it out. I think AV implicitly says this too, because if you think about this as a tube, and it's all in this tube, I've been implicitly using it earlier. Yeah, that makes sense. Okay. But it didn't have to be a square tube, honestly. Interesting. It's still used. Okay, I get it. All right, there's another thing I do want to mention. Unless there's a stagnation, the velocity must be tangent, because you can't have something going this way. And this is the reasoning for why over here. because you might be asking why, and then it's really just because it must be tangent. That's by definition, and you can't have a velocity without changing everything. Anyway, we're going to imaginary now. So imaginary says the potential plus I, I think it's a psi, must equal this version over here. So if you take a derivative, then you can catch me. This is actually just math. I think this is a review for you guys because we have done imaginary stuff before. I think you guys have, hopefully. And you get this form over here, which is a Cauchy-Riemann equation. There's actually, we're going to do the circle inverse, the region, circular, I forgot what it's called. Cauchy-Riemann, it's a Riemann circle. We'll do a Riemann circle later on, which we'll get to the just Klosky airfoil. Anyway, I'm getting tired. It's like 2 right now, 2 a.m. or something. I'm hallucinating, actually. Fun fact. This whole video has turned to a joke at this point. Anyway, who cares? No, only I'm watching it. Anyways, you can see you expand it, and you do this whole thing. And you get this formula to do this. But honestly, we're doing the same problem again, just for kicks of it. So if you do this and get this, and you put the u and I involved here, and u and I involved here, you get this form over here because of the expansion of the square, as you can see. And if you're asking, is this a coincidence how they created this? No. There's an actual whole entire way to solve this a long time ago. And how they do it is actually a method of imaging. So this is actually not by accident, but I would digress. I didn't explain that yet. So these functions are figured out somehow. And then actually it might be coincidence that it came so cleanly over here, but it's not coincidence that the functions of u and v were created how. And you can prove that by going and learning method of images, which I'm not done typing out, aka using AI and my paper notes and putting it into it and then reproducing it with cleaner, visuals is what I'm doing. And it works sometimes. It actually infuriates me sometimes because some of them are so wrong that I have to just say, okay, I'm gonna go to latex and fix everything up. Actually, half the time, it's like a 50-50 if it'll work, actually. Sometimes my handwriting is too messy for it. Sometimes it is just enough. Sometimes it's just garbage and it doesn't work. But and then you spend your time wasting. I don't know how many minutes I wasted on this. Anyways, so far, and then there's a different form. This diagram is from Dr. Sanchez over here. So you have UV and take a derivative over here, and you get this form. It's actually, it might be very much easier if I write it out. Like if I do this to my brother, I think it'll make more sense. That's why I'm going to bring another piece of paper and just show this part maybe, and then just start writing because it's probably easier. And especially since I have most of this memorized, it's not really a very big thing. So this is just a review. This is just changing it to Z form, which is imaginary. In any case, that's where we're at right now because I believe the next one is undone, method of imaging. Yeah, I'm going to do method of imaging, and then we'll start the next.